Hi students, in this video we're going to be covering the beginning of chapter 5, which has a lot of sort of introductory concepts, some vocab, things like that to set the scene for the rest of the chapter. So first, we're going to start with this little introductory video in class. If you're curious about it, feel free to look this up. If you go to the Veritasium channel on YouTube and search misconceptions about heat, you'll see it. And you're going to keep an eye out for what are some things you hear in this video that seem a little bit scientifically inaccurate. But again, we'll look at this in class. If you're watching this at home, you don't need to watch this part, but it may give you a laugh if you check it out. So, when we dive into some terms here, first off, our chapter is all about thermodynamics. We should probably figure out what that is. Thermodynamics is just the study of energy changes, if we're being very broad here. Now, energy is defined as the ability to do work or produce heat. Now, work is a concept you're going to hear a lot more about in physics. In our course, we're going to focus in more on the heat aspect of thermodynamics. So we'll be talking about heat energy and enthalpy and things like that throughout the chapter. But that term work, you're going to hear that come back later. When we're talking about energy, there are a number of different units out there. Some of the common ones you'll see in this chapter will be the joule. That's the standard SI unit of energy. Now, it is defined as a kilogram times meter square per second squared, which is kind of an odd jumble there, which is they just call that a joule instead. But if later on you're curious why sort of units can cancel out and leave you with other things, it's all based on how a joule is actually defined. But for us, you just need to know that it is represented with a capital J. And just like all of our other SI units, we could make any sort of version of that with our metric prefixes. So a kilojoule would have 1,000 joules in it and so forth. You'll also see calorie pop up a lot. Now, when we think calories, we're probably thinking of calories on food labels or, working out to burn calories, things like that. They are actually two different versions of the calorie. So the calorie we think of when we're thinking about food and working out and whatnot is actually a capital C calorie. So you can see it's abbreviated capital CAL. Unfortunately, that is spelled and looks exactly like a lower C calorie, but they are not the same. So one capital C calorie, the food calorie, has 1,000 of the little c calories in it. So when you hear capital C calorie or kilocalorie or food calorie, you'll also hear nutritional calorie. They're all the same thing. And those are the larger of the two. The little c calorie is smaller. Okay, now why do we have both of these? The short version is because the little c calories, if we put those numbers on food labels, they would be humongous. So it's a lot easier to say a granola bar has 120 capital C calories in it as opposed to saying 120,000 little c calories. So it's kind of just to make it look a little bit nicer, but ultimately, you'll see both of those. So some conversions you'll see between the calorie and the joule. One little c calorie is equal to 4.184 joules. That is in your reference book as well, so you don't need to memorize it, but you will see it pop up. And otherwise, I could convert between any of these as metric values. So again, like a kilojoule and a joule, a kilocalorie and a regular calorie, etc. Now, when we're talking about thermodynamics, there will ultimately be three different rules we will see, or three different laws, I should say. So our first law of thermodynamics is essentially the law of conservation of energy. It says that energy cannot be created or destroyed. It can only change from one form to another. So this is essentially wording-wise very similar to our law of conservation of mass, but now we're talking about energy being conserved. So we'll see that there will ultimately be two other laws throughout our chapter, but for now, we're just going to focus on that one. So when we say that energy can be converted from one form to another, what are some different forms? Well, one would be potential energy. Now, potential energy is energy based on sort of position or the arrangement, but in chemistry, that's essentially going to translate to chemical energy. So that's the energy stored in the bonds of various molecules and whatnot. So as a chemical reaction occurs, that potential energy is converted to something else. But again, potential energy in chemistry is thinking of that as your chemical energy, the energy stored in bonds. We also will see kinetic energy at play. So potential energy can be converted to kinetic energy. And kinetic energy is the energy of motion, right? That word kinetic, much like that prefix always refers to some sort of motion or movement, things like that. But in our course, again, in chemistry, although we say kinetic energy is the energy of movement, it is directly related to the temperature. So typically the temperature of something, or I should say its kinetic energy is proportional to its temperature. So as the temperature of a sample goes up, the kinetic energy of those atoms or molecules would increase as well. Now, temperature itself is really a measure of the average kinetic energy of all the particles in a substance. So, for example, if I have a sample of water and it's at 100 degrees Celsius, that's an average. So, many of those particles will be somewhere above or below 100, some will be at 100, but on the whole, most of those particles on average would have a temperature of 100 degrees Celsius, but there may be some below or above. That's why you can have water evaporate into the air at lower or higher temperatures than the boiling point, but certainly it wouldn't all evaporate if you were below the boiling point. But the big takeaway here is if kinetic energy and temperature are related, and kinetic energy is the energy of motion, that means that the higher the temperature, the higher the kinetic energy of those particles, and the faster those particles are moving. Likewise, the inverse is true as well. The lower the temperature, the less kinetic energy those particles have, and the slower they would be moving. The lowest you can go on the temperature scale is 0 Kelvin. 0 Kelvin is known as absolute zero, and that is the temperature where there is no molecular motion at all. So in other words, there's no kinetic energy. Okay, so just diving into that heat versus temperature idea a little bit more. Again, temperature is the average kinetic energy of all the particles in a substance. But if we're talking about specific particles or molecules in a sample rather than an average, we're talking about the heat of that particular particle or substance, that the heat energy involved with that particular thing. So when you see heat pop up in this chapter, that's going to be represented with a Q. I've seen both capital and lowercase. I typically use lowercase, but I have seen capital sometimes as well. And then temperature will be represented with that capital T. So just to think about these, we could have, if I have 2 glasses of water, one's full, one's a quarter full, and they're both at 50 degrees Celsius, they have the same temperature because they both have the same average temperature. However, that full glass is going to have much more heat because we have more particles there. So more particles, each with more heat energy. Collectively, we would have more heat in that glass, although their average temperatures are the same. So they are related, but not necessarily exactly the same. The more heat you have, though, the higher the temperature, and vice versa. Now, when you have 2 objects at different temperatures, what happens is we'll have heat transfer between those 2 objects. So the basic principle of heat flow is 2 objects at different temperatures, if you put them together in the same environment, will always reach the same temperature eventually. And we call that thermal equilibrium when they've reached the same temperature. So if you put, an ice cube near like a warm mug of coffee or something like that. Or even better, if you just put an ice cube in a hot cup of coffee, that coffee and that ice cube ultimately will end up at some temperature in between their original starting temperatures. And once they've reached that same temperature, kind of a lukewarm most likely, we would say that they have reached thermal equilibrium, or the system has reached thermal equilibrium. Another thing we could think about is, if they're reaching thermal equilibrium, how does that happen? It happens because heat is always flowing from the hotter or the warmer object to the cooler one. That is the only direction heat can flow, from hot to cold. Okay? Because heat is an actual concept of energy. Cold isn't actually anything. Cold is just the absence of heat. So you can't have coldness flowing, but you can have heat flow. So heat always goes from the hot object to the cold one. So if I have a mug in my hand, like we see in the first image, the heat from that mug is going to go to your hand, which obviously will hurt. But if you have something cold in your hand, like an ice cube, the heat from your hand is going to warm up that ice cube. Now your hand will start to feel cold, but your hand will start to feel cold because it's losing heat. It's giving up its heat to the ice cube. And that kinetic energy transfer, that heat transfer, is just going to keep going back and forth, well, not back and forth, but from hot to cold until both objects are at the same temperature, until they've reached that thermal equilibrium standpoint. Now, if you have a truly closed system, the amount of heat lost by the hotter object or the warmer object will be the same as the amount of heat gained by the cooler object, and vice versa, if you're not losing any heat to the surroundings. So you hear me mention that phrase surroundings and system, just to make sure we have those clear. The system is what you're studying. So essentially that's kind of the environment that's being studied, where the reaction's occurring or where the heat transfer is occurring. And then the surroundings are everything else. So the surroundings are everything else outside of the system that can still interact with the system. We can have heat flow between them, but it's not sort of what you're studying. So you can have both open and closed systems. An open system has much more freedom to interact with the surroundings, whereas a closed system is kind of self-contained and won't really interact. But we'll talk about heat flowing between the system and the surroundings throughout some of these earlier sections. The last terms we want to make sure we understand in this intro section are exothermic and endothermic. Now, you may have heard these terms previously somewhere in a previous science class or middle school, but just to make sure we know them. So exothermic, when we look at that, that prefix exo kind of sounds like exit. So this is when heat is exiting the system and going to the surroundings. So in other words, heat is leaving the system and going out to the surroundings, which in turn means the temperature of the system will decrease. Because if heat is being lost to the surroundings, the temperature of that system is going to go down. The opposite of that is an endothermic process or an endothermic reaction. Endo, that prefix, kind of sounds like enter. So this is where heat is entering the system from the surroundings. So in other words, heat is going into the system, which will make the temperature of the system increase. So we'll see some examples of both endo and exothermic reactions throughout our time, but some examples you see here, something like a fire is an exothermic process because as that fire burns, it's giving off heat out to the surroundings. So if you're sitting at a bonfire, you feel nice and warm because the heat from that flame, where the system is being transferred out to you in the surroundings and making you feel warm. Whereas if I have, an ice block on a sunny day, the heat from the sun is warming up that ice cube, so heat is being transferred to the system, the ice cube itself, which would warm up the temperature of that ice cube and in turn melt it. So exothermic reactions tend to feel warm to us out in the surroundings. Endothermic reactions will actually feel cold to us out in the surroundings because their heat is going into the system. Okay, so that was just a lot of terms we'll be hearing throughout the rest of the chapter. As always, if you have any questions on anything, though, please just reach out.